Oceanography An Outline. Objectives. After attending this lesson, the user would be able to understand basics of oceanography and the wide spectrum of studies carried out in the subject of oceanography. In addition, the concepts, methods, and developments of oceanography and its branches will also be understood. The role of oceanographers and the trends of research activities in the subject of oceanography will be known to progress further in this subject. Introduction. Oceanography is a science concerned with the physico-chemical characteristics of oceanic water, its depth, temperature, salinity, movements like tides, waves, and currents, flora and fauna found at various zones of seas and oceans. As it deals with the distribution and processes of these water bodies, it comes under earth sciences in general. The subject deals with the physical, chemical, and biological conditions of oceans. It is an interdisciplinary subject and an emerging area for marine engineering. It is the science of seas and oceans. Ever since people started sailing the oceans, attempts have been made to map them. Ptolemy's oldest map is an example. Ocean exploration began around 5000 BC with the first ocean diving and the first sailing vessels. Many advances that were made in the subject of oceanography were all through the great ocean expeditions and explorations. Scientific curiosity. Oceanographic exploration is a part of the subject of oceanography. Explorations helped in several ways to understand the ocean surfaces. Scientific investigations began with early scientists as James Cook, Charles Darwin, and Edmund Halley provided a lot of information. Ocean exploration itself coincided with the developments in shipbuilding, diving, navigation, depth measurement, exploration, and cartography. Ancient explorations refer to the period when people explored the ocean boundaries. Notable explorations include the Greeks, the Egyptians, the Polynesians, the Phoenicians, Pythias, Herodotus, the Vikings, and the Portuguese. During the period between the 15th and 16th centuries, deep diving became possible with the development of new diving suits and helmets. Ocean expeditions continued to sail with scientific curiosity, and the first submarine was also invented. The scientific understanding of oceans increased over a period of time, and people started studying the oceans with great interest and involvement. The marine explorations. The modern knowledge of the ocean began with voyages of discovery of Christopher Columbus, 1492 to 1494, Vasco da Gama, 1497 to 1499, Ferdinand Magellan, 1519 to 1522, and many others. They laid the foundation for global trade routes stretching from Spain to the Philippines in the early 16th century. The routes were based on a good working knowledge of trade winds, the westerlies, and western boundary currents in the Atlantic and Pacific. The early European explorers were followed by scientific voyages of discovery, led by, among many others, James Cook, 1728 to 1779, Charles Darwin, 1809 to 1882, Sir James Clark Ross, and Sir John Ross. All of them surveyed the Arctic and Antarctic regions from the Victory, the Isabella, and the Erebus. Edward Forbes, 1815 to 1854, studied the vertical distribution of life in the oceans. Bathymetric mapping. The beginnings of modern seafloor mapping coincided with the advent of systematic oceanographic observations. Some of the first recorded measurements of bathymetry were made by the British explorer Sir James Clark Ross in 1840, by the U.S. Coast Survey beginning in 1845 with systematic studies of the Gulf Stream, and by the U.S. Navy under the guidance of Matthew Fontaine Maury beginning in 1849. In 1872, the HMS Challenger expedition was the first to use fully the methods of bathymetry. The Challenger was the first vessel used to systematically record information about all the oceans except the Arctic, including their depths, circulations, temperatures, and organic life. In 1925, the Meteor, one of the oldest South Atlantic Ocean expeditions, used echo sounder for depth measurements using sound waves. In 1950s, the sophisticated precision depth recorders were invented and used. Remote sensing. Space oceanography encompasses a detailed oceanographic research and technological development resulting from manned and unmanned systems in the Earth's orbit. These systems observe and measure the oceanographic parameters such as sea surface winds, sea surface temperature, waves, ocean currents, and frontal regions, and provide real-time data for analysis. Remote sensing data obtained from satellites represents an indispensable source of information for oceanographers and fishery scientists. It enables researchers to monitor and study the marine environment as a fundamental basis to create a balance between sustainable environmental management and economic interests. Satellite oceanography. Satellite oceanography is a major milestone in the ocean analysis. The launching in 1978 of Seasat, the first oceanographic satellite, revolutionized measurements of physical properties of the ocean. Within a few years, the sea surface temperature, wave height, variations in sea surface contours, ice cover, chlorophyll content, and other parameters were measured and reported almost instantly from satellites. The sea surface properties that can be measured to useful accuracy from a satellite are the ocean color, sea surface temperature, SST, roughness, upwelling, and sea surface height, SSH. Oceanography, an interdisciplinary subject. Oceanography is an interdisciplinary science. It uses the principles and insights from biology, chemistry, geology, meteorology, and physics to analyze ocean currents, marine ecosystems, ocean storms, waves, ocean plate tectonics, and features of the ocean floor, including exotic biomes such as cold seeps and hydrothermal vents. Oceanography is a part of the subjects like physical geography, marine biology, marine geology, fishery biology, marine engineering, and marine geophysics. Subjects like historical geology, paleontology, and paleoclimatology are all interrelated subjects to oceanography. It is an interdisciplinary subject. Branches of oceanography. Oceanography is a very vast subject. It has several branches. The major branches of oceanography are physical oceanography, chemical oceanography, biological oceanography, geological oceanography, marine biology, applied oceanography, marine meteorology, and palaeooceanography. Although oceanography is the scientific study of the ocean, the subdiscipline of physical oceanography is principally concerned with the study of the structure and movement of water in the oceans. Study of physical setting of oceans. Physical oceanographic studies utilize a number of scientific specialities, and studies can encompass a diversity of technologies, from echo-sounding determinations of seafloor structure and seismic studies of movements in oceanic crust, to satellite estimations of current flow based on radar reflections and thermal imaging. Physical oceanography studies the many factors that influence the movement of ocean waters. Wind can push surface water, and the gravity fields of the sun and moon continually exert gravitational tugs that push and pull massive amounts of water in tidal cycles. Earth's rotation also contributes to the physical movement of water, as do density and temperature differences between oceans or between layers of water within the same ocean. 5 major oceans. The planet Earth is covered with 70% of water. All the oceans of the world cover about 361.1 million square kilometers and occupy a volume of 1,370 million cubic kilometers. The average depth of an ocean is 3,730 meters. All the oceans of the world are fully interlinked. They are the Pacific, the Atlantic, Indian, Southern Ocean, and the icy Arctic Oceans. The largest ocean among the oceans of the world is the Pacific Ocean. This ocean covers about 1/3 of the Earth's surface. The Atlantic Ocean is the second largest ocean of the world. It is the youngest of all the oceans and occupies 20% of the Earth's surface. The third largest ocean of the oceans of the world is the Indian Ocean. The waters around the Antarctica region are known as the Southern Ocean. It is the 4th largest ocean. Arctic Ocean is the smallest of the 5 oceans. All marine sciences deal with the study of all these oceans, their marine species, their ocean waves, and the other ocean life. Seas of the world. The seas of the world are almost hundreds in number. The notable seas are the Mediterranean Sea, the Caribbean Sea, the South China Sea, the Bering Sea, the Gulf of Mexico, the Okhotsk Sea, the East China Sea, the Hudson Bay, the Japan Sea, the Andaman Sea, the North Sea, the Red Sea, and the Baltic Sea. The Mediterranean Sea has an area of 2.9658 million square kilometers and an average depth of 1,429 meters. The Caribbean Sea has an area of 2.718 million square kilometers and a mean depth of 2,647 meters. The South China Sea has an area of 2.319 million square kilometers and a mean depth of 1,652 meters. The Bering Sea has an area of 2.2919 million square kilometers and a depth of 1,547 meters. Geological Oceanography. Geological Oceanography is a division of oceanography. It is mainly dealing with the basic concepts of lithosphere and hydrosphere. It includes the study of the oceanic crust, continental margins, ocean bottom relief, ocean basins, oceanic ridges, rift valleys, island arcs, seamounts, marine sedimentation, geology of corals, beach forms and processes, water masses, factors affecting ocean circulation, waves and currents, tides and energy, coastal erosion and drifting of sediments, sea level changes, depositional environments, and marine deposits. Geological oceanography is also concerned with the occurrence of oil traps and energy sources, tectonic movements, underwater eruptions, mud volcanoes, and impacts of tsunamis. The crust and plate tectonics. The crust of the Earth consists of rigid moving plates. These plates can move apart and create new crusts. They may slide past each other and create strike-slip faults. They may converge on each other by subduction, where a crust is consumed and the area will be shrinking. Most of these movements occur along narrow zones between plates where the results of plate tectonic forces are most evident. The next type is the transform boundaries. In this type, the crust is neither produced nor destroyed as the plates slide horizontally past each other. The plate boundary zones are broad belts in which the plate boundaries are not well defined and the effects of plate interaction are also not clear. All these aspects are studied in geological oceanography. Instrumentation. Instrumentation is vital to the study of physical oceanography. Determining wave height, water temperature, or current flow is impossible without a means of measurement. The height of the waves pounding onto the shore can be measured using conventional type of measuring instruments. Away from the shore, the wave height in deep water is measured using an instrument called as tide gauge. The tide gauge is immersed in the water and measures the weight of the water on top. Measurements in physical oceanography are done over a large range of scales. The measurements of ocean currents can vary from a few centimeters to the entire globe. Geodetic measurements. The present-day plate movements can be tracked directly by means of ground-based or space-based geodetic measurements. Geodesy is the science of analyzing the size and shape of the earth. Ground-based measurements are taken with conventional but very precise ground surveying techniques using laser electronic instruments. Since the plate motions are on a global scale, they are best measured by using the modern satellite-based methods. Space geodesy. The late 1970s witnessed the rapid growth of space geodesy. It is a term applied to space-based techniques for making very precise, repeated measurements of carefully chosen points on the Earth's surface, separated by hundreds to thousands of kilometers. The three most commonly used space geodetic techniques include very long baseline interferometry, VLBI, satellite laser ranging, SLR, and the Global Positioning System, GPS. Most of these are based on the technologies that were developed for military and aerospace research purposes. Among the three techniques, the GPS has been the most useful instrument for studying the Earth's crustal movements today. Morphology and relief of ocean floors. On the basis of bathymetric and other studies, the depth zones of oceans are divided into two major divisions called as continental margins and deep ocean basins. The continental margins include two major zones as continental shelf and continental slope. The continental shelves are adjacent to the beach zones. It is followed by the continental slope. The continental slopes are the inclinations towards the sea. From there onwards, there is a steep descent towards the interior part of the oceans. The deep ocean basins are the darkest depressions of the sea floor. Marine sedimentation. The major marine sediment types of ocean are of four kinds. The lithogenous or terrigenous sediments are the detrital sediment derived from the continental land masses. The biogenous sediments are the remains of dead organisms. The hydrogenous sediments are derived from the precipitation of dissolved minerals in water. The cosmogenous sediments are the dust and meteorite fragments derived from the outer space. The marine sediments of the oceans are sorted by their grain size. The gravels stay close to their source areas like river mouths. The sands move along the coasts by wave action. The silts and clays are suspended in the water column by wave action and are carried out into the deep sea. All the biota may ingest into the fine sediments and make fecal pellets. Sedimentation patterns are analyzed in geological oceanography. Marine mineral resources. Oceans and seas are the sources for food, energy, and mineral deposits. Huge volume of mineral matter are deposited in ocean bottoms. It is estimated that 40 pounds of gold and 200 pounds of lead are present in dissolved form in every 1 cubic mile of ocean water. Vast resources of petroleum, coal, and natural gas lie buried deep below oceans. The oceans are the treasure houses for polymetallic nodules, cobalt-rich crusts, and polymetallic massive sulfides. Minerals derived by mechanical erosion from continental rocks are concentrated as placer deposits. These minerals contain heavy metallic elements like barium, chromium, gold, iron, rare earth elements, tin, thorium, tungsten, zirconium, and nonmetals including diamonds, lime, siliceous sand, and gravel. Coastal zone processes. Coastal zones are very sensitive zones. Continental shelves and near-shore waters comprise about 5% of the area of the world. In spite of this, 2/3 of the world's population thrives near the coasts. Throughout human history, people have been attracted towards the coasts because of the moderate climates, food, commercial and recreational opportunities they provide nearer to the beach. Coastal ecosystems are good habitats for innumerable flora and fauna. Coasts are an interface between the lithosphere and the hydrosphere. Time immemorial, beaches are considered to be the best places for tourism, fishing, mariculture, water transport, recreation, sporting, social, political, and community interactions. Geomorphology of coasts. Every continent or island is bordered by a long or short coastline. Coastline is the line separating the land and sea. Coastal zones are the transition zones between terrestrial and marine habitat. They form an interface between land and oceanic natural processes. Coastal areas also are varied in their topography, climate, and vegetation. Some are sandy beaches, rocky shores, with or without tidal inlets. The climate of a coast are controlled by the land and sea breezes, and the humidity controlled by marine water. Waves, tides, and currents are very powerful geomorphic agents. The erosional and depositional work of the sea waves can create many spectacular landscapes along the borders of the continents. Studying the coastal landforms are interesting aspects in coastal geomorphology. Physical oceanography. Physical oceanography deals with the physics of the ocean. It describes the physical processes influencing the oceans and coastal regions, the interaction of the ocean with the atmosphere, the distribution of oceanic winds, currents, heat fluxes and water masses, oceanographic exploration, evolution of scientific concepts, physical setting of seas and oceans, dimensions, seafloor, bathymetry, databases. Sound in oceans is an important phenomena for oceanographic explorations. Atmospheric influences. Physical oceanography is also concerned with the atmospheric influences, wind systems, wind stress, oceanic heat budget, fluxes, heat transport, temperature, salinity and density, light in the ocean, and absorption of light. The dominant forces for ocean dynamics include the types of flow in oceans, conservation of mass and salt, equations of motion with continuity, viscosity, turbulence, mixing and stability concepts. The response of the upper ocean to winds, geostrophic currents and the hydrostatic equilibrium, wind-driven ocean circulation called as ocean waves, vorticity and deep circulation in the ocean, equatorial processes including the El Nino effects are all studied in physical oceanography. Radiations and ocean's heat budget. Atmospheric heating of oceanic water masses is an important aspect in oceanography. Solar insolation is the primary source of energy. Most heat input to ocean water occurs near the equator, and the least input occurs at or near the poles. It makes the fluids to move. The fluids in motion are affected by Earth's rotation. Temperature T and salinity S combine to produce volumes of water with specific water characteristics. Temperature, salinity, and density. Oceanography deals with the distribution of temperature, salinity, and density of oceanic waters. They vary with reference to space, time, and depth. Their geographical distribution is an important aspect to tackle the problems of oceans. The oceanic mixed layer and thermocline, measurement of temperature, measurement of conductivity or salinity, measurement of pressure, light in the ocean, and absorption of light are some of the essential aspects of study in this subject. Salinity is a measure of amount of dissolved material in water after correcting for gases and organic material. It is an important property of study in oceanography. Equations of motions. Oceanography deals with the dynamics of water masses and their motion. These are controlled and analyzed by developing the equations of motion, the dominant forces that are acting for ocean dynamics, the types of flow in the ocean, conservation of mass and salt, and the solutions to the equations of motion. It also deals with the equations of motion with viscosity, the influence of viscosity, turbulence, mixing of water masses in the oceans, and their stability. In fluid dynamics, we typically confine our attention to the movement of small fluid elements. To derive the equations of motion for a fluid, we consider the balance of forces acting on such fluid elements. The fluid element feels the sum of all the forces, and its motion is given by Newton's second law of motion. Oceanographic studies includes all such equations and parameters related to them. Currents, waves, and tides. Oceanography is also the study of currents, waves, and tides, geostrophic currents. It analyzes the hydrostatic equilibrium of water masses. The surface geostrophic currents are analyzed based on altimetry and hydrography. A lot of wind-driven ocean circulations are also analyzed in this subject. Ocean waves are the never-ending actions on the surface of oceans. The linear theory of ocean surface waves, non-linear waves, wave forecasting, and measurement of waves are the basic aspects of study. In addition to these, the study of coastal processes and tides, theory of ocean tides, tsunamis, storm surges, and tidal predictions are also included in oceanography. Oceanographic circulations. Ocean circulation is related to the large-scale movement of waters in the ocean basins. The prevailing winds drive the surface water circulation, and the cooling and sinking of waters in the polar regions drive the deep water circulation. The surface water circulation carries the warm upper surface waters poleward from the tropics. The heat is dispersed along the way from the waters to the atmosphere. At the poles, the water is further cooled during winter and that water mass sinks in to the deep ocean. This is especially true in the North Atlantic regions and along Antarctica. Deep ocean water gradually returns to the surface nearly everywhere in the ocean. On reaching the surface, it is carried back to the tropics and the cycle begins again. This global circulation pattern is called thermohaline circulation. Oceanography deals with the deep circulation of water masses in the oceanic floors. The driving forces of surface ocean circulation and surface ocean currents and upwelling. Observations of the deep circulation are a major part of the subject. Biological oceanography. The basic ecological concepts are central to many studies of biological oceanography. The study of marine life, habitat, interactions, abiotic environment, phytoplankton and primary production, zooplankton, migrations and changes, energy flow and minerals cycling, marine food chains, food webs, nectans, marine reptiles, mammals, seabirds, mariculture, benthic plants and animals, intertidal environments, beaches, coral reefs, estuaries and mangroves are all studied under biological oceanography. Deep sea ecology and marine pollution are also the other two major important areas of study under biological oceanography. Biological zonation. It is necessary to understand the basic ecological divisions of the ocean. The marine environments are subdivided into two major divisions as pelagic and benthic environments. The word pelagic means open sea and benthic means bottom. The word pelagic refers to the ocean water column from the surface to the middle of the oceans. The word benthic refers to the deep ocean floor. In the open sea, the zone extending from the high water to the low water zone of the coastal belt up to a depth of 200 meters inside the sea is called as the neritic zone. Divisions of pelagic zone. The pelagic zone is further subdivided into epipelagic zone, extends up to 200 meters from the ocean surface. Mesopelagic zone, extends up to 1000 meters below epipelagic zone. Bathypelagic zone, extends from 1200 to 4000 meters below the ocean surface. Abyssopelagic zone extends beyond 5200 meters and up to 6000 meters from the surface. Hadal pelagic zone, beyond 6000 meters and up to 10,000 meters below the ocean surface. Divisions of benthic zone. The deep ocean benthic zones are further classified into supra-littoral zone, on the beach, high water line. Littoral zone, high water to low water line region. Sub-littoral zone, low water line to 200 meters depth on continental shelf. Bathyal zone, 200 meters to 3000 meters depth zone. Abyssal zone from 2000 meters to 6000 meters depth on continental slope region, and hadal zone lying beyond 6000 meters up to the end of 1000 plus meters depth in the deep oceans. Environmental conditions. The pelagic environment supports the life of planktons and nectans. It is seen that the epipelagic zone is the sunlit zone. Enough amount of sunlight penetrates into the top layer of oceans for plants to carry on photosynthesis. The mesopelagic zone is known as twilight zone. This is a dim zone where little light penetrates, but not enough light for plants to grow. The bathypelagic zone is known as the midnight zone. This is the layer between 1000 meters and 4000 meters depth where there is no light penetration. The abyssal zone is the pitch-black bottom layer of the oceans. The oceanic water present in this zone is almost freezing and its pressure is immense. The hadal zone is the last deepest zone. This is the most inhospitable zone of the oceans. All these aspects are analyzed in oceanography. Population of the seas and oceans. Oceans are a rich treasure house of economic resources. Oceans are full of various kinds of vegetation and organic life. Some of them are very small or tiny, and some of them are large animals. Marine food resources are unlimited. Fisheries are inevitable aspects in human survival. Marine life ranges in size from microscopic one-celled organisms to the blue whale, which may measure up to 30 meters long. Ocean plants and plant-like organisms use sunlight and the minerals in the water to grow. Sea animals eat these organisms and one another. Marine plants and plant-like organisms can live only in the sunlit surface waters of the ocean, which is called the photic zone. The photic zone extends only about 100 meters below the surface. Beyond that point, the light is insufficient to support plants and plant-like organisms in the sea. Animals, however, live throughout the ocean, from the surface waters to the greatest depths. All these aspects of marine life are studied in oceanography. The word plankton in Greek means wandering or drifting. Planktons are the floating plants or organisms. Planktons are mostly of microscopic in dimension. There may be phytoplanktons, which may be denoting the plants, and zooplankton denoting the animals. Zooplankton are drifting animals and are usually small but grow to fairly large sizes. Nectons are free-swimming animals. Some of the phytoplanktons are passively transported by the currents in the sea. Fish, squid, and marine mammals are the major nectons found in oceans. Biological oceanography deals with all these aspects. Chemistry and nutrient cycling. Oceans are the mega marine ecosystems. In these ecosystems, many life thrive due to the presence of nutrients. The term nutrient cycle refers to the movement and exchange of organic and inorganic matter back into the production of living matter. This process is regulated by the food web pathways that decompose the matter into mineral nutrients. Ecosystems recycle locally, converting mineral nutrients into the production of biomass. The cycles of several key elements, phosphorus, nitrogen, sulfur, carbon, and possibly iron and silicon, are essential aspects studied in biological oceanography. Nitrogen, phosphorus, and silicon are called biolimiting nutrients since they limit the amount of life in the ocean. Nitrogen, phosphorus, and silicon are exhausted first in the surface waters since each is essential to the growth of phytoplankton, the microscopic algae that float with the ocean currents. These things are discussed in both chemical and biological oceanography. Biological productivity. Phytoplanktons are the major primary producers in the pelagic realm. The rate of primary production in plant mass is called as primary productivity. The total weight of all organisms in a given area or volume is known as the biomass. The physical controls of primary production are studied in biological oceanography. The properties that are controlling the primary production in ocean shallow waters are light, physical forces, abundance of nutrients, and temperature. All these factors vary with reference to seasons and location. This part is an essential part for economic resources point of view in oceanography. Marine biology. Marine biology is yet another division of oceanography. It is the scientific study of the life in marine waters, ecosystem components, energy flow, productivity, trophic levels, fishery biology, aquaculture, mariculture, growth and biological processes, forms, communities, migration, etc. Some of its specialized branches concern natural history, taxonomy, embryology, morphology, physiology, ecology, and geographical distribution. Aspects of particular interest in marine biology include marine biogeochemistry, ecology of marine populations and communities, marine ecophysiology, behavioral biology of marine organisms, development and life cycles of marine organisms, biochemistry and physiology of marine organisms, evolution of marine organisms, population genetics of marine organisms, marine conservation and technology developments in marine biology. Marine biology also deals with the pollution and the impacts of human influences on marine waters. Chemical oceanography. Chemical oceanography is the study of everything about the chemistry of the ocean, distribution and dynamics of the elements, isotopes, atoms, and molecules. The chemistry of the ocean is closely tied to ocean circulation, climate, the plants and animals that live in the ocean, and the exchange of material with the atmosphere, cryosphere, continents, and mantle. This ranges from fundamental physical, thermodynamic, and kinetic chemistry to two-way interactions of ocean chemistry with biological, geological, and physical processes. Chemical oceanography includes processes that occur on a wide range of spatial scales, from global to regional to local to microscopic dimensions and temporal scales, from geological epochs to glacial, interglacial to millennial, decadal, interannual, seasonal, diurnal, and all the way to microsecond time scales. Much of chemical oceanography describes the cycling of the chemical elements both within the ocean and with the other spheres of the Earth system. It encompasses both inorganic and organic chemistry and includes studies of atmospheric and terrestrial processes as well. Dissolved salts in seawater. Seawater contains about 3.5% by weight of salt as sodium chloride. The salinity of seawater varies with reference to space, time, and depth. The combination of salinity and temperature has a major influence on the ocean currents and their behavior. 6 major ions compose more than 99% of all dissolved material in seawater. They are chlorine, sodium, sulfate, magnesium, calcium, potassium. All major ions in seawater are conservative. Their ratios do not change. All dissolved materials have residence times varying from hours, nitrous oxide, to millions of years, sodium. Oceanography requires the continuous measurement of seawater salinity for its analysis. Gas molecules exchange continuously between sea surface and atmosphere. Seawater has many different gases dissolved in it, especially nitrogen, oxygen, and carbon dioxide. It exchanges these gases with the atmosphere to keep a balance between the ocean and the atmosphere. This exchange is helped by the mixing of the surface by wind and waves. At the ocean-atmospheric interface, gases are added to seawater by diffusion and wave action. Gas composition at the ocean surface is in equilibrium with atmosphere. Gas composition also changes with time and depth in the oceans. Solubility of salts. The major ions and dissolved gases in water, nutrients, conservative elements, gas exchange, mass balance, residence time, processes, life in the oceans, productivity, ocean's biological carbon pump, sediment traps, ocean carbonate system, oxygen mass balance, chemical equilibrium and solution chemistry, free energy of reactions, acids and bases, deep ocean fluxes, redox chemistry, hydrothermal circulation, chemical tracers and radionuclides are all studied under the subject of chemical oceanography. Chemical oceanography attempts to analyze all the geochemical interactions between the global oceans with lithosphere, with atmosphere and the biosphere. It deals with the chemistry of seawater, geological controls in various chemical distribution, components of marine sediments, and the geochemical controls in biological production. Geochemistry. Marine chemistry and geochemistry concerns chemical and geochemical processes operating in a broad range of study areas that include the oceans, the solid earth, the atmosphere, marine organisms, polar ice sheets, lakes, meteorites, and the solar system. Chemical oceanography deals with the geochemical interactions of sediments with seawater and interstitial waters, geochemistries of volcanic and geothermal phenomena, chemical exchanges between the ocean and the atmosphere, geochemical cycles of carbon, oxygen, sulfur, nitrogen and other elements, isotopic geochemistry of the solid earth and meteorites, and the atmospheric trace gas chemistry. Oceans and climate change. The oceans and atmosphere interact constantly, both physically and chemically. They interact by exchanging energy, water, gases, and particles. This relationship influences the Earth's climate on regional and global scales. It also affects the state of the oceans. As greenhouse gases trap more energy from the sun, the oceans are absorbing more heat, resulting in an increase in sea surface temperatures and rising sea level. Although the oceans help reduce the climate by storing 1/5 to 1/3 of the carbon dioxide that human activities emit into the atmosphere, increasing levels of dissolved carbon are changing the chemistry of seawater and making it more acidic. Changes in ocean temperatures and currents brought about by climate change will lead to the alterations in climate patterns around the world. Effects of climate change. Warmer waters cause coral bleaching, which in turn negatively impacts the entire coral ecosystem. Many species will be forced to migrate so they can maintain the temperature conditions they need for feeding and reproduction. Alteration to water temperature can directly impact development, age of sexual maturity, timing of spawning, growth, and survival of most fish and cephalopods. Decreased upwelling due to warmer waters means that fewer important nutrients from lower in the water column will make it to the surface of the water. As warming ocean waters impact life within the ocean, humans and the industries dependent on them are likewise impacted. Rising greenhouse gases causing increased atmospheric warming cause polar ice to melt. As seawater warms, it expands. Likewise, as glaciers and polar ice melt, sea levels rise. Changes in ocean temperatures and wind patterns will result in overall climate change that will affect and alter the oceanic currents and their patterns. The burning of fossil fuels that is increasing greenhouse levels in the atmosphere will also affect and alter the chemical composition of seawater, making it more acidic. These are essential aspects in oceanography. Palaeooceanography. Palaeooceanography is the study of the history of the oceans in the geologic past with regard to circulation, chemistry, biology, geology and patterns of sedimentation and biological productivity. Palaeooceanographic studies using environment models and different proxies enable the scientific community to assess the role of the oceanic processes in the global climate by the reconstruction of past climate at various intervals. Palaeooceanographic research is also intimately tied to paleoclimatology. Radiometric dating of ocean rocks is an important aspect in this subject. Marine carbonates record the strontium isotopic composition of the seawater in which they are formed. They give good indications for many oceanographic analysis. Research methods in oceanography. Geological oceanography and coastal geology are closely related yet distinct disciplines. Geological oceanographers study the rocks and structure of the ocean floor sediment that covers them, and the processes that formed them. Coastal geologists focus on these structures and processes in a coastal environment. Major research programs in biological oceanography examine cycles of carbon and other biologically critical elements such as nitrogen, phosphorus, silicon, and iron. Other important areas of study include understanding linkages between different levels of the marine food web, from phytoplankton all the way up to fish and marine mammals. Researchers may deal with issues that affect the life such as water pollution, overexploitation of fisheries, and harmful algal blooms in oceanography. Biological oceanographers. Biological oceanographers study all forms of life in the oceans, from microscopic plants and animals to fish and whales. In addition, biological oceanographers examine all forms of oceanic processes that involve living organisms. These include processes that occur at molecular scales, such as photosynthesis, respiration, and cycling of essential nutrients, to large-scale processes such as effects of ocean currents on marine productivity. In addition to making scientific observations, the biological oceanographer uses a variety of models to study the biology of the oceans. Theoretical models are used to examine problems in biological oceanography that cannot be answered through direct observation and measurement. Conclusion. The ocean is a vast body of water. It is very difficult to understand many of the aspects and processes happening inside the oceans. Oceanographers study all the physical, chemical, and biological conditions of the seas and oceans. They also discover the hidden treasures of the sea beneath water. Oceanographers analyze how the ocean water moves and how it affects the atmospheric conditions. Marine biologists explore and investigate how marine organisms thrive in the sea. Marine geologists investigate how various forces shape the seafloor, sedimentations happen, and tectonic forces play their role on ocean bottoms. Oceanographers use various sophisticated equipment on scientific vessels, ships, or submarines and satellites to monitor the dynamics of all oceans. Maritime engineers study the design of vessels and their applications with modern tools and technology. The Navy of any country has to thoroughly understand the oceans, continental margins, and their conditions for defense purposes. It is here we have to understand the world oceans in a detailed way. Energy from the ocean has several forms. The ocean tides also provide energy. Petroleum and natural gas are the ocean's most valuable energy resources. Medicines have been produced from many forms of marine life. The ocean helps keep the Earth's environment healthy. Oceanography is an interesting subject of study in earth and atmospheric sciences.